Chi-squared tests. One of the last ones that we learn in AP statistics, and we are jumping from quantitative data and working with means to multiple proportions. So looking at categorical data, but something that we cannot do with just the z-test for proportions or the z-intervals for proportions. So there are three different tests. There's a lot that's the same about each of them, which we'll highlight, but then the couple of differences and sort of the basics of it. So the goodness of fit test, which I believe is used in AP Bio, is when you're given a particular claim and you want to compare as to whether or not yours is true. So one of the most popular questions with this is looking at the distribution of M&Ms. They are not uniformly distributed. Different colors have higher ratios for whatever reason to make it look more appealing. And even regular M&Ms versus peanut versus some of those other not so great flavors change the proportions. And so it would be a matter of if we had some M&Ms, everyone had a sample, and if we looking at our sample of M&Ms broke down, if they were supposed to be 24% blue, I think 20% orange for each of the different colors, how did our sample break down? So we're not looking at just one color in particular, which is why we can't just use the z-test for proportions, but we're looking at the entire distribution. And so we're not going to do 6 different tests, one for each color. We're looking at it as a whole. Does it mostly fit? So one might be a little bit off, that might be balanced by another one. But in general, does that particular one work? So you need those percent breakdowns for what the population should be given to you in order to do that. And then homogeneity or homogeneity, however you want to pronounce it, and the independence, aka association test, show up in two-way tables. So for the homogeneity, it's the idea that we are saying that they're the same throughout those two populations, whereas in independence or association, we're questioning whether or not there's a relationship between the two of them. And we'll do this with quantitative data with regression, but this again is for our categorical data. For these tests, we have our overall test, which is what we're used to. But something that's different with chi-squared than with the others is because we have multiple categories, and whether it's in goodness of fit, where we have like those colors of M&Ms, or one of the cells of a two-way table in the homogeneity or the independence, there's something called follow-up analysis that is done after you calculate the test statistic. If we find that one value in particular contributes an awful lot, so let's say we got an awful lot of one color and then all of the other ones were under so slightly just to balance it out, that would be the contributing factor. And then we would question why in this one particular category did we see something like that happen. And so that's all that the follow-up analysis does. It's easiest when we have the technology of the test to work through, which we'll get to with each of the three. So also the same between all of them. Chi-squared is no longer a bell curve. So that normal condition or approximately normal, we're not taking a look at anymore. You can see the visual from the book, very strongly skewed to the right with 1 degree of freedom, and then it becomes less and less skewed as the degrees of freedom increase, sort of the way the t-distribution approached the normal curve as the degrees of freedom increase. So our test statistic will only ever be positive, and we same way with means, have to rely on degrees of freedom if we're using the table and thinking about what the curve will look like. Goodness of fit is an easy one. It's just categories -1. And so that is with the colors, again, if there are 6 different colors of M&Ms, then we have 5 degrees of freedom. And so whenever we would do that in class, even if we ended up with different numbers of M&Ms, everybody had the same number for degrees of freedom. The condition that's replacing the normal condition, so we're still thinking of it in terms of large counts. There's something we have to calculate called the expected counts. If they're all at least 5, then that's when we know that this curve is appropriate to use, that our calculations will be accurate based upon that. So to work through each of the 3 tests to kind of talk about what's the same and what's different, starting in the state step. One of the hardest things with chi-squared is making sure you're identifying the correct test, and we'll practice that a little bit at the end. Goodness of fit is one where you could write it out if you wanted to in proportions, and then the alternative is saying that at least one of them is different from what was stated. I would recommend always writing everything out in words. So even for this goodness of fit, and this is the M&M example again, if we just said that the distribution of color proportions in our sample matches the stated distribution, and then again, it only takes one to be significantly off from what it's supposed to be in order for that alternative to be true. Not all 6 of them have to be incorrect. So for homogeneity, this example dealt with quitting smoking, and if you used like a Nicorette gum or a patch or a pill or some combination of them. And so there's no difference in how effective each of those treatments would be, or there is in fact a difference. And then the association independence, I don't like to say independence because our null hypothesis is a statement of no difference. So if you say there's no relationship between student smoking habits and their parents, or there's no association between them, then your null hypothesis sticks with that no idea. And then the alternative is that there is in fact one. If you say independent, that's no association. So we'd be saying in the null that they're independent variables, and then in the alternative, they're not independent variables. And so it's totally up to your preference, whatever that might be. And this context came from a problem that was like, never did it, tried it once, you know, smokes a pack a day kind of thing. And then if that was related at all to what the parents did, so it was asking the same categories with the parents. So that one population and addressing, like, I was never a smoker, but both of my parents smoked. Unfortunately, one of them still does. The other one's celebrating a large anniversary here soon, 35 years without. And so then just is there a relationship there? So plan steps, state plan to conclude. Plan, very similar to what we had before. We still want it to be random, either sample or experiment. We call it large sample size so that it's all encompassing with the chi-squared. And again, that deals with expected counts, and then independent as we have always known it. Expected counts are pretty easy to find. We'll deal with those particulars. Goodness of fit is by far easier, the easiest one. And then it's just kind of tedious, but the homogeneity and association are done the same way. So a couple of things when you're calculating, just mistakes that we sometimes make, because we're given proportions, we want to sometimes use them, but the test statistic always deals with the counts. So the numbers that we had, and they should be whole numbers for observed counts, but your expected counts can have a decimal point. You don't have to round it to be a whole number. And then when we're looking at the large sample size, it's the expected counts. Sometimes we look at the observed counts that are given to us, but it is in fact what should be happening, because again, that's the, if the null is true, then that's what that component is based on. So this test statistic, I just pulled this image out of the book. Observed minus expected, so how far away is it, squaring it to make everything positive, and then dividing by the expected count. And this is because it gives us an idea relative to what it should be, how far off is it. So they're not all equally weighted, and then we add each of those components together. It looks a little bit different on the formula sheet, is all that bottom tip is addressing. So computer output will be very helpful, as will the calculator. So as before, there's a chi-squared CDF that we can use in working through this, and there is also a chi-squared test on the calculator. And at this stage of the game, we probably all have newer calculators or have updated operating systems. So you have a chi-squared GOF test listed there as well. We do need goodness of fit we'll work through in a list, and then we use matrices for the other two. So this one, an example out of the book, dealing with the matrix here, the first value that you see, if you look across the first row where it says French, for the French entree, the 30, 39, 30 are all the observed counts. And then under Italian, it's the 11, 1, 19. And then under other, The next number, the 34.22, so sort of that second row with each one, those are my expected counts. And then the chi-squared contribution, the part of the test statistic, is the third one. So you can see the French entree didn't vary much from what was expected, that 30 to 34.22 only contributed to the chi-squared to test statistic 0.521. But if you look dead center, the Italian entree with the French, we observed 1 but expected 9.57, so that's pretty high. So out of our chi-squared statistic, which is listed at the bottom, the 18.279, that 7 was the biggest contributor to it, and then the Italian was the next one. Those two alone make up most of that test statistic. 4 degrees of freedom, which we'll explain when we get to the table problems, and then the p-value is given to us, which is nice. So in the conclusion, the only thing we're doing is adding the follow-up analysis. Otherwise, everything's the same. So we reject the null if the p-value is too small, so if it falls below our significance level, our alpha level, or we fail to reject it if it's too big, interpreting it in context. So if the null hypothesis is true, which these ones get to be a little bit easier, maybe because we've done so many significance tests at this point, or just because we are writing the hypothesis in words already, and so it helps to write the conclusion, and then adding the follow-up analysis, which is what's new. Okay, and then, again, one of the hardest parts, because so much of this is the same, the conditions are the same, the do step is very, very similar, the conclusion, the way that's written out. We'll practice a little bit figuring out which of the tests we should use. Goodness of fit visually usually stands out for us because it's the only one that's not in a two-way table, and also the only one where we're given values as to what it's supposed to be. Homogeneity comes from 2 or more populations. So in the wording of the question, recognizing that there were 2 or more, or just saying along the line somewhere, we're wondering if there's a difference between them. And then association independence comes from 1 sample, so 1 population, but then they also tend to question whether or not there's an association that's there. So a few examples out of the book. This outliers was really interesting with Malcolm Gladwell. Depending on when you were born, was there evidence that you made it big, basically? So because of the way that they do age cutoffs, people that tended to have birthdays earlier in the calendar year essentially had more practice and kind of had a leg up on other people. So are they uniformly distributed throughout the year or not? Is there a relationship between gender and allergies? And then again, another treatment one. So do the treatments have the same success rates or are they somehow different, which is what the homogeneity is getting to. So we will look at all 3 of these and take a look at the calculator. But last thing, because we'll do that within each of them, the table is here. So this chi-squared table that we hadn't used yet, again, kind of like the t distribution. So the degrees of freedom are down the left side, and then the tail probability is across the top. And so what we can do is take a look at, for instance, the one example that had the computer output with the French and Italian, there were 4 degrees of freedom. We would go through this row and try to figure out where in this row our test statistic fell. And so the best we can do is typically say that it falls between 2 values, which is why technology is going to be a huge help. Whether you do the full-fledged test, which of course I recommend on the calculator, or you're using the chi-squared CDF to figure out exactly what it is. But this is basically saying that that area of 0.001 or the top 0.1% is marked off by that test statistic at 18.47. So if our value is greater than that, the p-value is a little bit lower than that because those tail areas get smaller and smaller the bigger the chi-squared value gets. So again, very similar to what we've done before. The hardest part will be figuring out which one is which, but we'll take a day and look at each of the 3 different types in the full 4 steps. State plan do conclude, so we can see how to piece it together and how to use the calculator.